Okay, so thank you everybody. Sorry for the technical problems. So we have today TRINIDAD LANTAñO, who will talk about her work on mediated entanglement and the Lense-Thirring effect. She's finishing her PhD at the University of Ulm in the group of Martin Plenio and Susanna Huelka. And the floor is yours. Thank you.
Thank you so much, Marius. Thank you for the invitation and the hospitality. You guys all are very nice. You have a very nice group of people, so I'm very happy. And also it's very appropriate, I think, to discuss mediated entanglement here with this crowd, because here is a very active topic. Well, as Mario said, I'm Trini, I am at Ulm, and today I want to tell you about a not so recent anymore work that we have on gravity-mediated entanglement, but with a twist. So I'm going to give a little spoiler before so you know where I'm going to get to. Usually, the experiments in gravity-mediated entanglement, they consider the interaction between two masses, but the Newtonian interaction with a hat on, right? They first quantize it. And then they look at the entanglement between the position degrees of freedom. So we look at the different observables. So we look at the angular momenta degrees of freedom, which will interact through general relativistic contribution that is called frame dragging, or it gives rise to the frame dragging effect, we would say. And then this would entangle the angular momenta degrees of freedom, which is a different thing to look at. And this is also with the hope that we see new effects, richer, maybe more quantum effects in gravity. We'll see. We will discuss these things. Also, it comes with its own challenges, of course. So the overview of the talk, first I'm going to give a motivation. I think most of the things I'm going to say you've heard 1,000 times here. So the Feynman, the Chapel Hill, the whole thing. So I'm going to repeat it a bit if you don't mind. I'm going to explain the Newtonian entanglement, so the so-called the Bose-Marletto-Vedral kind of setup. Then I'm going to introduce our work properly, the frame dragging entanglement, and some feasibility analysis and the coherent mechanisms to then finalize with the theoretical implications of it. So some open questions, really. Okay, so let's get to it. Motivations. Quantum theory allows for superpositions, right, of degrees of freedom in matter. So we could have spins, superposition, we can have positions. And this motivated also a very natural question by Feynman in the 57 in Chapel Hill, where he made this Gedanken experiment. He says, okay, I have a ball which has kind of a sizable gravitational field. I put it in superposition. How does a test mass behave in response? What is this gravitational field doing of a particle in superposition? I think now Marcus Aspelmayer probably measured the gravitational field of a smaller ball than what Feynman proposed, so this is crazy. So it is, of course, not an easy topic. It's not unanimous. At the time when Feynman did propose these experiments, he also got some discussion going on. I think Bundy and other people were also criticizing that quantizing, you don't have to quantize the Newtonian potential, right? You should quantize the radiative degrees of freedom, etc. And now it's not also a paper by Marius. It's not so clear how you split between radiation and longitudinal degrees of freedom. So it is not obvious that it will tell you something about gravity, or it will, looking at entanglement, will tell you that gravity is quantized. There were these two papers that you, of course, know by Bose collaborators and Marletto and Vedral, 2017 in the same issue of PRL. And they started, let's say, a research line, yeah, a whole field, a lot of papers came out after this, but because it caught the attention of people. So before, there were some proposals on gravitational mediated entanglement, 2005 by Lindner and Perez. They already put forward an experiment to see gravitational mediated entanglement. And then Caffrey and Taylor, 2013. So there were other proposals before. These are not the first proposing entanglement mediated by gravity, but they, it's true, they have a very concrete setting also, Bosé and collaborators. They have a very concrete setting that might be feasible in some years, okay? And here I explain it a little bit. We have, right, two particles, massive particles in superposition of their center of masses. They interact only through gravity, which is a challenge, of course. And the interaction happens, or is say, described only as a unitary evolution with a first quantized potential. You just put heads on the position. And this unitary evolution will generate different phases, accumulations of phases, depending on the branches. So different branches will have different distances between them, and this will give you different gravitational interactions, which ultimately will result in entanglement. So one can just compute the negativity or any entanglement measure, and you will see that it depends directly on the delocalization of the particles, okay? So as long as you have particles that are delocalized in space, you put them in, you know, interacting with the Newtonian potential, you will get entanglement. And heated discussions were ignited. I like to put this as comment on the comment in response to the comment. And that's why I say it's a very nice phenomena that happened here. People have, of course, opinions, and it's very good that there are discussions, because it's not obvious. So the issue of the quantization of the electromagnetic field itself, we see that there were many hints experimentally before the ultraviolet catastrophe, and quantum field theory was very successful. But it was not until this very compelling experiment by Clauser, where a single photon was measured, that it was not unanimous and accepted that the electromagnetic field should be quantized. But detecting a single graviton is, of course, out of the question for now, technologically, because the coupling is so weak with respect to the coupling of electromagnetism. So then we come back a bit to the entanglement discussion. Can we measure a consequence of the gravitational field being quantized instead? So this is what generates the problems, right? The discussion, the consequence, because it could come from, as many people put forward, from other theories that could explain this entanglement. So yeah, this is good examples. Well, this is not entanglement, okay, but we know that it's a subtle matter, because a classical field can generate coherence and phase shift in interferometers. We know Rabi oscillations, they are routinely done in NMR, for example. The Cow effect, we know that is, I don't know if you guys are familiar with the Cow effect. Yes, I don't have to explain it. But this can be completely explained with a classical gravitational field. Gravitational Aharonov bomb, very appropriate, because it was partially also, the observation was done by Peter Hasenbaum here at Ikoki, so great. Also, the normal Aharonov bomb experiment can also be explained with a classical electromagnetic field. So a theoretical challenge for us, right, because there are experimental challenges, but for us theoretician is to design an experiment that cannot be explained by any, I will add, reasonable classical theory, okay? So this is our challenge, and for this, it's crucial that we define a framework to talk about classical and quantum. So what are we talking about? We have to be in the same language. And for this, I would say that the LOCC argument is a good starting point. People, of course, and yeah, I agree. And the LOCC argument doesn't say anything about fields. It only concerns channels, communication channels, okay? So this comes from information theory, quantum information theory. Basically tells you that if you have two, I think you had a talk on, yeah, on how to separate, oh no, it was how to, LOCC, let's say, locality in Hilbert spaces is different from locality in space-time, etc. So this is true, it's very subtle, but this only concerns channels, okay? So a map of a state that maps you to another state. And if your operations available are local operations in classical communication between in two particles in a separable state, then you will always map separable states to separable states, always. So then the argument goes, if we had a separable state at the beginning, we have a channel that is opened by gravity or is mediated by gravity, and we see entanglement, then some operations outside of the LOCC set happened. Could be non-local gates, could be exchange of quantum communication, quantum bits, or both. So this is the safest way to phrase it, I would say, and this is what it is and nothing else. And maybe somebody could draw an analogy with or a parallel with the with relativistic locality, but for now it's just something very pragmatic about channels. Okay. So within entanglement in spatial degrees of freedom, so Newtonian entanglement, I will call, or mediated entanglement, one can see two groups. So one can see the Gaussian ones, that people that consider two delocalized states but Gaussian, so harmonic oscillators, and non-Gaussian, which is what I just explained, that you have sharp, or not even sharp, you can also have a superposition of coherent states that are cat states, but these are non-Gaussian states, and they both will give you entanglement at the end, surprisingly with the same rate that that is proportional to the delocalization. Okay, this is a paper, I didn't put it by Martin also, but they both give you entanglement with the same rate. And as I said many times, they all share that is the Newtonian limit. Okay, and we know that what the Newtonian limit is static, is instantaneous, is near field. So it's every approximation is the Newtonian limit. And for this reason, the conclusions that one can get are limited to this regime. And this has been widely debated, right? What can you say if you only see, because at the end, the entanglement you will see will be due to the underlying theory that you have, right? But the description we're doing is by hand is with the Newtonian potential, that's true. But this is the reason why it's so debated, because we're considering only a Newtonian potential, it's first quantized. So in an attempt to, so for us it was more an exploratory attempt to say, okay, what happens if we go a bit further, if we consider different degrees of freedom. Really, this was at least my motivation first, so to look not at position degrees of freedom, but at angular momentum. And luckily, there is an interaction that couples this, and this is the frame dragging interaction in general relativity. So it goes like this, is also called the gravitomagnetic sector or effect. We have, after, linearized gravity, static approximation, so you have a Laplacian there, and you consider also the 0I elements of the stress energy tensor. They are non-zero now if you have angular momentum, so they will be populated, and they will source a metric. They will source gravity. Right, this is mass currents that source gravity. And we see this equation looks exactly like electromagnetism. I think Marius was talking about this at lunch. That is it's true. It's only in a gauge, in a certain gauge, that it resembles electromagnetism. And for the same reason, one can say, okay, it will have the same effects physically. One can expect to see analogous effects. And indeed, so we have also, we can do a multiple expansion with, as you do with the vector potential, and you can get a dipole-dipole interaction. What we see here. So this was first obtained by Lense-Thirring, Thirring, who was here. He was director of this institute, or not this institute, the university, because Ikoki didn't exist, but he was here. And well, Robert Wald also treated this very nicely. So we have this kind of a dipole-dipole interaction, but between the angular momenta, and of course with a different coupling, which is very small. You will, first thing that people always tells me, it's very small. First thing Martin told me when I told him, this is very small. But wait for it, because there is a trick. So the trick is to have two spheres that are rotating really fast. So they are rotating so fast that you can compensate this very small coupling with an L square here. So let's see here numbers. If we rotate them to the tens of gigahertz, 10 gigahertz regime, so 10 to the 7 hertz, which is possible in theory. So we also did this feasibility analysis in the paper, right, that they are not going to get broken because of the rotation. So it's possible in principle to rotate silica microspheres to the 10 to the 7 hertz. This will give you a angular momentum quantum number of 10 to the 23. So this is macroscopic, this is mesoscopic, I don't know, very big. 10 to the 23. Then here you will get, it's not hard to see that if you act on an angular momentum eigenstate, you will get an L square out. Always somehow you will get an L square, which is 10 to the 46. Then this coupling, which you have to believe me, is like 10 to the minus 47, 48, something like that. It will get of order 1 of order 1. So, of course, depends on the times you consider. But then it gets comparable to the Bose-Marletto-Vedral proposal, let's say, because you have this huge angular momentum, these huge rotations. And here we can see, so if we start with initial state, here I made kind of a drawing in the, you can call it block sphere. It's not a qubit, but you can draw this kind of decay states here that they look like a ring. I don't know if you guys, you understand what I mean with this? Yes? So this is the variance of it that gets spread in the, so you have complete certainty in the LZ component, so M, it's an eigenstate, but then, since it's a finite space, you get all the uncertainty spread in a ring in Ly and Lx. So then we will have initial states like this, and if we put them in contact and we quantized, just as the other people quantized the Newtonian interaction, unitary evolution, we will see entanglement building up. Okay, this doesn't say a lot, the numbers, you know, it's von Neumann entropy. This is not something you would see in the lab. I'm not an experimentalist, but this much I know, that you don't see the von Neumann entropy directly in the lab. And for this, we do propose a witness, which is the violation of an inequality in angular momentum variances, if you were wondering. But this is only to see that entanglement is indeed building up. And it will, of course, depends on the preparation of the initial state. So consider, so M is M times 10 to the 22. So this is, for example, m equal L, because L is 10 to the 23. So this is m equal L, and then you have different values, m equals 0, for example. M equals 0 is a very interesting case in which you don't have a superposition anymore. So you have L0, L0 here. And you can see in the entanglement buildup, so it's the black one, it's not the lowest one, actually. One is not expecting that, but this is kind of interesting. So it's m equals 0 here, then it goes down, and then it goes up, and this is m equal L. Okay, I think I already made my point here. This in defect too small. If one puts in the numbers that Bosé and collaborators give in their paper, one sees that they fall in the same plot, okay, in the same order of magnitude as our preparation. This is with m equals 0, this is with m equal L. So really it's comparable, okay? I don't know. I didn't. You don't need it. No, you don't need a superposition. You will have entanglement. You will have entanglement for sure, but I just don't know what rate of entanglement. It's not obvious to me, but you will get entanglement. Yes. Yes. Mm-hmm. I hear you. Yeah. No, it's not working. I can repeat the question.
It's not amplifying, it's just for the
Now it's working.
for the stream.
Now,
Ah.
okay. So yes, Miguel was saying what happens if you do not have a superposition of the angular moments, and you're saying you would get entanglement anyway, but you don't know how to calculate it. Why
No,
is
I
it more
do.
difficult? Okay.
No, you will. I just don't know exactly where would it fall, like in this plot. In this plot, what would be the rate? I would say might be close to L equals 0. But you will get entanglement because if you see, so if you put here, let's say, imagine this in an evolution operator. So you can expand the evolution operator, 1 plus I, whatever. So effectively, you will have the action of this Hamiltonian, yeah, because this is very small, so you can just expand it. Then if you put an eigenstate here of angular momentum, here you have ladder operators. So the ladder operator, for example, for L0, this term will give you 0 because L0, Lz and m equals 0 is 0. But the ladder operators will create states, will populate states. So this is a different kind, I don't want to say different kind of entanglement, but this is a different process because in the Newtonian case, you have just phases, relative phases. Here is not phases, you're populating other states. You're making transitions possible in principle. So it's a bit different and it's interesting in that sense.
I guess the question is sort of naively, we're all theorists here. No, there is one experimental.
Good, you should ask things.
It sounds difficult to create a macroscopic superposition of these states, right? Because there is some macroscopic thing going in superposition. This M can be 10 to the 23. And so if you do not have to do that, why are you considering the superposition to begin with?
No, it's true. And in the paper, we do say that it would be better to do it with L0 alone. We consider it just to, I don't know why we did consider. Actually, this is an ansatz that we could have just not taken. That's true. Maybe to be more similar to the case, because at the beginning you don't know what you're going to get. So to be more similar to the case of a Newtonian entanglement, where you have 4 branches. So we didn't know what we were going to get. but you don't need it. That's true. Yeah, you don't need it. Although it was not easy to argue with the referees, we had to take a bunch of stuff out because it was not obvious to them why it was easier or not so challenging to prepare L0 than superposition, because it's not obvious, apparently. Everything is hard, yeah. Yeah. But for us too, it was, yeah, you don't have to do a superposition, but anyway, you have to prepare an L0 eigenstate. It's anyway super challenging. So, okay, some decoherence channels for the experimentalist. You're not going to love our analysis, though. It's from theoreticians. So, but you have to do this feasibility analysis. This is good. So we had fun with this, actually. So we're going to put some of the decoherence channels we consider. There were more, but didn't want to bore you with it. So there is, for example, electromagnetic interactions. These are the ones that nobody likes for these GME experiments. So these silica microspheres will have some nuclear spins anyway, so they are neutral, okay? Yes, but they will have some nuclear spins. This is more or less what they have. Then one can estimate how much is the dipole-dipole interaction, but now really the electromagnetic dipole-dipole interaction. And estimating it, this is with respect to gravity, so this is the magnetic dipole-dipole with respect to gravity. You'll have something like this, where p squared, p is the polarization of the spins. So if you have a very small polarization, I don't know, 10 to the minus 6 already, oh, great, 10 to the minus 5. But I don't know how realistic is that. So we, in case we say, okay, an electromagnetic shield is required, then people might argue this introduces more problems. Maybe a shield, in the case of Newtonian entanglement, it does have some Casimir forces. Here, okay, I don't talk about this in this talk, but something interesting is that maybe heuristically you can understand Casimir forces do not affect, at least in the first orders, the entanglement in angular momentum degrees of freedom, because it's position. It's a Casimir forces is x to the something, to the 7 is position, and here is entanglement between angular momentum. So one can do the calculations, see that at the end everything commutes, and they will not affect this. We will have other problems, but not so much the Casimir interactions. Decoherence due to collisions, so one can compute the the entropy, no, not the entropy, the negativity, sorry, because it's a mixed state. One can see during one collision even, so collisions are terrible, super detrimental. These are the quanta that are going to be exchanged due to the collision, okay? The M quanta. This is nothing. Of course, a collision will exchange more quanta, but to see that it falls pretty quickly, already with 6 quanta, you're almost in 0. So we are requiring that the probability of collision must be way below 1 in the time that we consider. It has to be. One collision will kill everything. So we need quite extreme conditions here. These separately have been achieved. So this 10 to the minus 18 Pascal actually has been achieved in anti-proton experiments. This is not so bad. Quantum computers, they do it all the time, this 0.1 Kelvin. But together, of course, is the challenge. Thermal radiation, this was the more fun thing we did because, so we had to, of course, come up with a model to describe how the spheres are going to interact with a thermal bath, with an electromagnetic field. So then at the end, we decided for this interaction, so they can actually be effectively described with a dipole, with an electric dipole. This could even be measured. And the electric dipole, we know that interacts with an electric field in such a way, so you second quantize it, of course, and then ignore that, but it's just to show you can get a master equation starting from the Hamiltonian. You just trace out, some selection rules. You get to a master equation that will tell you how the L and the M numbers change due to temperature. So there is exchange of quanta because of the bath, and then you will have this nice plot, which does what we expect, right? So unitary evolution is the blue, and then if you add temperature, the entanglement, the negativity will fall. Of course, it's not so bad as the collisions. We can tolerate some temperature, but of course it falls. And this is something new, but nobody really cares about this because it's in the appendix. But this, nobody, is the first time we see a master equation that describes angular momentum decoherence. So it's also nice, but we just have it in the appendix. Yes, it's nice derivation. So, okay, one can do, of course, all this feasibility analysis and talk about how to make the experiments, but more importantly, why bother, right? One has to ask this question. Will it tell us anything new about gravity? Anything more interesting than what already people is trying, which is Newtonian gravity? And I think yes. This is a completely unexplored thing. We do not talk about it in our paper, but it's something that could be a follow-up, like an outlook. So in the, I call it BMB, oops, but this is fine, the Bosé-Marletto-Vedral experiment, yes. The initial state here is a superposition of semi-classical configurations. So we have, yeah, it's understandable. We have either here, 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 or here. It's very obvious what are the configurations in the experiment. And we also, because of this, one can have an interpretation such as this paper by also Marios and Rovelli and others where they, no, actually only you and Rovelli, that there is an interpretation from the gravity-mediated entanglement that comes as a consequence of classical configurations being in superposition. So the field being in superposition will give you this effect, this phase, which comes from some difference in proper times. Okay, there is a clear interpretation there because you can map the configuration to different classical configurations. In frame dragging, it becomes a bit more obscure, which makes it nicer, and because we have some work to think about. In the case of extremal states, so when you have some kind of a GAZ state, right, or yeah, extremal superpositions, each one is a semi-classical state. One can think about it is a coherent spin state. It minimizes the uncertainty relation. Good. So one can also have a picture imagining that this is a superposition maybe of space-time, scarce space-times or something like this. In the case of L0, L0, this becomes more interesting because they are highly quantum, okay? And highly quantum in the sense that, okay, first of all, the vector, the angular momentum vector is 0. The expectation value, obviously. So classically, you would not expect to have an effect because you don't have angular momentum. It's 0. Wigner negativity, to put it in more quantitative matters, this is not from me. This is from a nice paper that I always like to go back to. They measure the Wigner negativity of different spin systems. So if you want to check that out, this paper has them all. You see that here the state L0, they take L to be 80, it has high Wigner negativity. It's not the highest. Something in between is the highest, but it's high. So then Wigner negativity is usually regarded as a measure of non-classicality. It's very well proven in the harmonic, let's say, bosonic case, in coherent spins of light and etc. There is very well proven because it also, yeah, it's a measure of non-classicality there, very well established. But in spin systems, it's not so well studied yet. And we can see that some states, such as this one, have high Wigner negativity. So it's interesting, we have the opportunity with such a setting to study the action of general relativity, so general relativistic contribution, on a highly non-classical states, highly quantum states. So we might see something more quantum mechanical that gravity does. We don't know yet, but it gives room for work, right? And this is something we're looking at. So summary, community is still debating. Community is really many communities, but this is nice. So there is a good debate around what the Newtonian gravity-mediated entanglement means. We propose to look at other observables, another interaction that might give new theoretical interpretations and also experimental challenges to test the quantumness of gravity. So with this, I thank you so much for your attention. And yes, these are the... also, we wrote an essay that to the Gravity Research Foundation that you can check out. Thanks.
Thank you very much, Trinidad, for the nice talk. So whoever has questions, I have to give him this thing.
Cool. Thank you for the talk. I think it's a very interesting idea of using frame dragging to try to witness this mediation of entanglement through gravity. It does seem that the main challenge is these collisions you mentioned, right? So in the sense that the very few collisions can really drag down the entanglement between the particles. So I'm just trying to understand a little bit more like where these collisions are coming from. So it's I assume that you have like particles that are somehow trapped into different positions. They're placed in these rotation things. So what is colliding with them in this
Air
case?
particles.
Air particles. All right, from this vacuum that you have. So basically like that's why you need such a low pressure to be able to decrease it so much.
Yes.
Okay, I see. Thank you. And then just to, well, the other question is, have you looked at basically trying to combine this technique with some of the other techniques in the more, in the previous attempts of gravity-mediated entanglement? Because it's I mean, sure, you are basically shifting some of these challenges, right? And maybe actually the sweet spot is to try to have some kind of in between the two up to some extent. Do you see any way in which it would be possible to basically combine these two to actually really improve the numbers? And I'm saying this because, like, for instance, the under effect, there are, I mean, various known numbers everywhere, but people are coming from different directions trying to optimize different aspects of the thing, and then ideally the idea is that, well, if we combine all of these, then maybe we can actually find numbers that are reasonable, right? So it's very good to have this in gravity-mediated entanglement, but it would be even better if we could actually combine these. So in the sense, let me just formulate the question, it's like, do you see this as an orthogonal approach, or do you see this as something that can be potentially combined to actually improve the numbers?
It's a good question. I never got asked this. Well, these are two different observables that get entangled, or degrees of freedom. So in this sense, I don't think they are orthogonal, but they are different. So we look at different signals, let's say. So we look at the violations of angular momentum, uncertainty. They look at other things, spin witnesses. So for now, I don't see how to mix them.
But maybe if you can think of the Gaussian case, in which, like, of course, like in 3D, it's possible to have a harmonic oscillator, which has rotating states, and then you can talk about angular momentum. At the same time, these are delocalized, so maybe it's possible to, you know, play a little bit with the connection between them in some context like this. But
maybe if you have a Gaussian that is rotating, something like that. I mean, you will. So what you want, I guess, is to get both terms in the Hamiltonian to act on something and generate entanglement. Maybe you can have entanglement between position and angular momentum, degrees of freedom. I don't know, because okay, you want to keep, you will have the Newtonian potential, you want to keep it there, plus the frame dragging potential. This is how you would mix them. And then you need a state to act on, in which both act non-trivially. So in this case, yeah, maybe you can mix them, but I don't see how that make it easier. Like that would make it even harder, maybe it's even more challenging.
I mean, I guess it depends on the observables that can be accessed to measure entanglement between position and momentum here and position and momentum there. But I think, I don't know, it's maybe it's a...
Well, I could think about that. Yeah, maybe.
So, small comment on what Rick asked, because Emil, correct me if I'm wrong, I think we have seen a proposal that has a spinning mass in a superposition of states spinning one way and another way, and the particle going in a superposition of trajectories around it. So maybe that's something that combines the two. But I think there's something here that's even more exciting, which is what you said about not being able to interpret this as a superposition of spacetimes. And I'm very curious, because having the background of GME in mind, also when I first look at the state, I would say, so you have a superposition of 4 configurations, so you create 4 different spacetimes, and Lense-Thirring is different in each one of them. What is happening in the m equals 0 case?
Yes, indeed. Oh, no. Wait, I'm going to go back. This is a good question. We don't know.
Is it even too non-classical to approach? And
is something, so okay, in principle, you have your Lx and Ly are pointing somewhere in the XY axis. Yeah, they are somewhere here, but the uncertainty is so big that it averages to 0. So yeah, I don't know. This is an open question.
An equal superposition of all of them in a sense, and you can say that...
Maybe, yeah. You could maybe write it down as superposition of Lm's in the Y and X. No, yeah, in the other basis, in the orthogonal basis. Yes.
I have forgotten my angular momentum from mechanics, but would you then, if that's the case, and you can do a nice change of basis, be able to say, you didn't put spacetime in a superposition of 4 states, you put it in a superposition of...
Infinity, would say, I think. Yeah.
But is there a middle ground also to this? Because like here with the Wigner negativity, the maximum M states, you can see them as a superposition of spacetime, so completely on the left, you can say...
No, this is not a superposition. This is just 80, 16.
No, I'm saying that the plus minus 80, you can see as a superposition of 4 spacetimes, no?
Yes.
You would call this semi-classical in a sense. Just by themselves.
Yeah,
so
this is only one. This is only one. Yes, only if you take only one decay states like this, you put 80, 80, this is LL.
Okay.
LL has Wigner negativity 0. And then this is L0, which is this guy. Yeah, but it's not a superposition. Yeah.
I'm curious. I mean, okay, we've been discussing. At some point, we can also stop and keep discussing.
Go. I have time.
Before I say something, actually, does somebody else have a question? Do you know?
So here, you were arguing that because these states have a negative Wigner function, then they are not classical. But doesn't this apply to the semi-classical states that you were showing before? They also have a negative Wigner function.
Which ones?
Go back. Yeah, the BMV experiment.
No, okay, each one doesn't. Each one is no, the cat state, true. It has a negative Wigner function, these two. But I'm talking about the different components of the superposition. So this one itself is a Gaussian state. It It's positive Wigner function.
Yeah, sure.
Yeah.
So what? I mean, you don't prepare in that state. You prepare in a superposition.
Yeah.
It's
Okay.
actually non-classical. So
I know what you mean, but it's for the interpretation of it, so that you can interpret it in, for example, in the paper that they have, which you can look at the branches only, and you can interpret it as classical configurations being in superposition. And then you have this nice proper time difference of proper times interpretation. It's just because of this. I know what you mean. You prepare the state that is true. This has Wigner negativity, but each one is classical or semi-classical. Okay. Yes. Yeah.
So what would be the analog in the BMV case to the m equals 0? Would it be something like very wide or something like this? And then it's two wave packets that are very wide somehow, and then because of this width, they interact, but not too sharply peaked things with a phase?
I think the nice thing about this is that there is not an analog, a direct analog. Because if you have a wide thing, it's still a semi-classical. It's just very delocalized, but it's always finite, the localization it has. So in the case of having the sphere, you have the maximum, you have like a maximum delocalization. In the case of a planar XP, you can have infinite. So you never will reach a maximum delocalization. So
And I can always make it.
yeah, you can make it bigger, but it will still be a coherent state. Yeah. Yes, true. But yeah, I mean, like if you fix the angular momentum, then you have a space that is a subspace. Yes, you fix it, and yeah. In that case, I think there is no analog, I would say.
So I think it's like something like if you have a superposition of many nearly orthogonal Gaussian states, then you could potentially see something that is analogous to this at 0, right? Because it's like it's something that really has no Flash analog in the sense, but it's this very different from just like, for instance, having a squeeze state that is very squeezed, because that is still like a Gaussian state in that case. So I think it's there has to be some sort of analog, but it has to be some sort of like something that is a superposition of many nearly orthogonal Gaussian states. So maybe a bunch of like
Rick, sorry to interrupt, but it's not going through also, your comments.
No, I just wanted to put my
I think we should wrap it up.
Yeah, let's wrap it up also.
I'd like to continue chatting, but maybe, yeah, let's do it offline. So let's thank the speaker again.
Thanks. I'm going back. Yeah, I wanted to show the QR, but I was going the other direction. Yes.